Imagine standing outside on a clear night when the full moon hangs bright and silver in the darkness above you. You've seen this sight thousands of times, Earth's familiar companion glowing steadily in the star-filled sky. But tonight, something extraordinary begins to happen. A subtle shadow starts to creep across the moon's bright face, as if an invisible hand were slowly drawing a curtain across a cosmic window. Within an hour or two, that brilliant silver disk transforms into something almost otherworldly. A deep, rusty red orb hanging in the darkness like a glowing ember suspended in space. Hello, and welcome to the Sleepy Astronomer. Tonight, we're exploring one of the most beautiful and accessible cosmic phenomena you can witness from your own backyard, the lunar eclipse. Unlike so many astronomical events that require special equipment or perfect timing, a lunar eclipse unfolds slowly and gently enough that you can step outside, look up, and watch an entire world change colour before your eyes. If you're joining me for the first time, welcome to our gentle journey through the cosmos. And if you've travelled with me before to explore the quiet wonders of space, it's wonderful to have you back among the stars. Our journey tonight will take us through the elegant geometry that turns our home planet into a cosmic shadow maker, exploring how three worlds, Earth, Moon and Sun, align in space to create one of nature's most spectacular light shows. We'll discover why ancient civilizations saw dragons devouring the moon, why some eclipses turn the moon blood red, while others leave it barely dimmed, and how modern astronomers use these shadowy encounters to unlock secrets about our planet's atmosphere and the moon's ancient history. There's something deeply moving about lunar eclipses that goes beyond their visual beauty. Unlike solar eclipses, which can only be seen from narrow paths on Earth's surface, a lunar eclipse is visible from anywhere on the night side of our planet. When the moon turns red, millions of people around the world are looking up at the same transformed sky, sharing the same moment of wonder. It's a reminder that we're all passengers together on this spinning world, all looking out at the same cosmic neighbourhood. The mathematics of eclipses connects us to some of humanity's earliest scientific insights. Ancient astronomers used eclipse observations to measure the size of Earth and Moon, to track the motion of celestial bodies, and to realize that we live in a universe governed by predictable patterns. Every eclipse is both a spectacle to enjoy and a gentle lesson in the clockwork precision that governs the motion of worlds. From the comfort of modern understanding, we know exactly when eclipses will occur and what causes them. But there's still something wonderfully mysterious about watching our familiar moon slowly disappear into Earth's shadow, then emerge transformed into an alien red orb that seems to belong in someone else's sky. It's a reminder that even in our well-mapped solar system, beauty and mystery can appear on any clear night when the geometry of space aligns just right. So, settle in, get comfortable, take a slow, deep breath, and let's begin our gentle exploration of lunar eclipses. To understand what an eclipse truly is, we need to step back and imagine something that happens every single day, something so familiar we rarely pause to consider its cosmic significance. Right now, as you listen to these words, you're casting a shadow. The light from your reading lamp, the glow from your screen, or perhaps the soft moonlight filtering through your window. All of it is being blocked by your body, creating a region of darkness that follows you wherever you go. Your shadow is a simple thing, really. Light travels in straight lines, and when something gets in its way, your hand, your head, your entire body, it creates a dark space on the other side. The shadow is not made of any substance. It's simply the absence of light, a place where photons cannot reach because something solid stands in their path. This basic principle, playing out on a cosmic scale, is what creates eclipses. Now, imagine scaling up this everyday phenomenon to astronomical proportions. Instead of your body casting a shadow on the wall, picture our entire planet, 8,000 miles across, spinning silently through space, casting a shadow into the darkness behind it. Earth's shadow is enormous, a cone of darkness stretching nearly 1,000,000 miles into space, tapering to a point far beyond the moon's orbit. Most of the time, the shadow passes unnoticed through empty space, invisible against the cosmic dark. But occasionally, about twice each year on average, our moon drifts into this shadow, and something magical happens. When the moon enters Earth's shadow, we witness a lunar eclipse. For a few hours, our familiar silver companion dims and often takes on an otherworldly red glow, transformed by the very air we breathe into something that seems to belong in an alien sky. It's a reminder that we live on a world, not just in a place, and that our planet participates in the grand dance of light and shadow that governs all motion in space. But lunar eclipses are only half the story. There's another type of eclipse, one that perhaps stirs even deeper emotions and has shaped human culture in more profound ways. This happens when the shadow casting roles reverse, when our moon passes between Earth and the Sun, temporarily blocking our view of our nearest star. These are solar eclipses, and they unfold in a completely different way than their lunar cousins. During a solar eclipse, the moon's much smaller shadow races across Earth's surface at over 1,000 miles per hour, creating a narrow path of darkness that can stretch halfway around the world. If you're standing in this shadow's path, you experience something that has moved people to tears, changed the course of battles, and inspired some of the most beautiful writing in human literature. The sun, our source of light and warmth, disappears behind the moon's dark disk, and for a few precious minutes, day becomes night. The fundamental difference between solar and lunar eclipses lies in whose shadow you're experiencing. During a lunar eclipse, you're watching the moon move through Earth's shadow. You're observing the eclipse from outside the shadow zone, looking at its effects on another world. During a solar eclipse, you're inside the moon's shadow yourself, experiencing directly what it means to have a world step between you and the sun. This difference in perspective creates entirely different experiences. A lunar eclipse unfolds slowly and gently. You can watch it safely with your naked eyes, as the moon gradually dims and changes colour over the course of several hours. The experience is contemplative, meditative. You have time to make a cup of tea, call a friend, come outside and watch, or simply lie back and observe the slow transformation taking place above your head. A solar eclipse, by contrast, is intense and brief. The approaching shadow creates an otherworldly twilight that makes birds return to their roosts and flowers begin to close. The temperature drops noticeably. Animals often exhibit confused behaviour, unsure whether night is falling or some other inexplicable change is occurring. And then, when the moon completely covers the sun's bright disk, the solar corona becomes visible. The sun's ethereal outer atmosphere, normally invisible against the brightness of daylight, suddenly revealed as a shimmering silver crown around the dark silhouette of the moon. The emotional impact of these two types of eclipses tends to be quite different as well. Lunar eclipses inspire a quiet sense of wonder. There's something soothing about watching the moon transform slowly in the darkness above, like watching a flower bloom in time-lapse photography. The red colour that often appears during a lunar eclipse, caused by Earth's atmosphere bending and filtering sunlight, creates a sense of mystery without fear. The moon may look different, but it's still clearly the moon, still in its proper place in the sky. Solar eclipses, however, can trigger more primal emotions. When the sun disappears from the sky, even when you know exactly what's happening and why, something deep in the human psyche responds with awe and sometimes unease. This is our source of light and life temporarily vanishing, leaving only a ghostly corona in its place. Ancient peoples often interpreted solar eclipses as omens or supernatural events, and even today, witnessing totality can be an overwhelming emotional experience. The visibility patterns of these two eclipse types also differ dramatically. A lunar eclipse is visible from anywhere on Earth's night side. Roughly half the planet can see it simultaneously. If you're experiencing night when the moon enters Earth's shadow, you can simply step outside and look up. No special travel is required, no precise positioning. The moon, hanging in space 240,000 miles away, presents the same face to everyone on the night side of Earth. Solar eclipses follow much more restrictive rules. The moon's shadow on Earth's surface creates a path of totality, typically only about 200 miles wide. If you want to experience a total solar eclipse, you need to be in exactly the right place at exactly the right time. Miss the path by even a few miles, and you'll see only a partial eclipse. Interesting, but not the transformative experience of totality. This is why eclipse enthusiasts often travel thousands of miles to position themselves in the shadow's path, and why some people become eclipse chasers, following these paths of darkness around the globe. There's something poetic about the fact that total solar eclipses are only possible because of an extraordinary cosmic coincidence. The sun is about 400 times larger than the moon, but it's also about 400 times farther away. This means they appear almost exactly the same size in our sky, an alignment so precise that the moon can just barely cover the sun's bright disk, while leaving the corona visible around the edges. This perfect size match is temporary in cosmic terms. Millions of years ago, when the moon was closer to Earth, it would have appeared larger and blocked the corona entirely. Millions of years in the future, when the moon has drifted farther away, it will appear too small to completely cover the sun. We live in a brief window of cosmic time when perfect solar eclipses are possible. The mechanics of both types of eclipses rely on the same fundamental astronomy. Earth orbits the sun once each year, while the moon orbits Earth roughly once each month. Most of the time, these three bodies are not precisely aligned. The moon's orbit is tilted slightly relative to Earth's orbit around the sun, so the moon usually passes a bit above or below the line connecting Earth and sun. But about twice each year, the alignments become nearly perfect, and we enter what astronomers call eclipse seasons. During an eclipse season, which lasts about 35 days, at least one eclipse will occur, and sometimes two or even three. If the alignment happens at new moon, when the moon passes between Earth and sun, we get a solar eclipse. If the alignment occurs at full moon, when Earth passes between the moon and sun, we get a lunar eclipse. The precise timing and location determine whether any given person will be able to witness the eclipse. But the celestial mechanics unfold with clockwork precision. Understanding eclipses was one of humanity's first great astronomical achievements. Ancient civilizations that learned to predict eclipses gained not only practical advantages, knowing when these dramatic events would occur, but also deep insights into the structure of the cosmos. The ability to predict eclipses proved that the universe operated according to mathematical laws, that the motion of celestial bodies followed patterns that human minds could understand and anticipate. The ancient Greeks used eclipse observations to make remarkably accurate calculations of the Earth's size and the Moon's distance. During a lunar eclipse, they could see the curved edge of Earth's shadow passing across the Moon's face, providing direct evidence that our planet is spherical. By timing how long it took for the Moon to pass through Earth's shadow, and knowing the Moon's approximate size, they could calculate the relative sizes of Earth and Moon with impressive precision. These early astronomers also realized that eclipses provided a way to synchronize observations across vast distances. If astronomers in different cities observed the same lunar eclipse, they could compare their local times of the eclipse phases and use the differences to calculate geographical distances and longitudes. Eclipses became cosmic clockwork, allowing ancient scientists to map both the Earth and the heavens with increasing accuracy. There's a gentle irony in the fact that eclipses, which once terrified ancient peoples as supernatural events, became some of our most reliable tools for understanding the natural world. The same phenomena that inspired myths of dragons devouring the sun or moon proved to be exquisitely predictable events that revealed the mathematical harmony underlying celestial motion. Beauty and terror transformed into knowledge and wonder, a reminder that often our fears dissolve when we learn to see the patterns that govern what initially seems chaotic or supernatural. The dance of shadows that creates eclipses connects us to the vast scales of space and time that govern our solar system. When you witness an eclipse, you're seeing direct evidence of worlds in motion, Earth spinning on its axis, the Moon orbiting our planet, our entire Earth-Moon system travelling around the Sun. These motions, invisible in our daily lives, become visible during eclipses as shadows sweep across space and worlds temporarily darken or change colour. Perhaps most remarkably, eclipses remind us that we live in a universe where beauty and precision interweave on cosmic scales. The same gravitational forces that keep the Moon in orbit and Earth circling the Sun also create the precise alignments that generate eclipses. The same physics that governs the behavior of light, traveling in straight lines, creating shadows when blocked, operates identically whether we're talking about shadows on a wall or shadows cast by worlds across millions of miles of space. As we begin to understand the fundamental nature of these shadow dances, we can start to appreciate the subtle differences between the various types of eclipses we might witness. Not all lunar eclipses are created equal. Some plunge the Moon into deep darkness, while others barely dim its silver light. The shadows cast by worlds are not simple black circles, but complex regions with fuzzy edges and varying depths, creating a range of eclipse experiences that depend on the precise geometry of Earth, Moon, and Sun at the moment of alignment. If you've ever held a flashlight in a dark room and watched your hand cast shadows on the wall, you've already discovered one of the fundamental truths about light and shadow that governs eclipses across the cosmos. Move your hand closer to the flashlight, and the shadow becomes larger and sharper. Move it farther away, and the shadow grows smaller and more diffuse. Hold up different objects, a pencil, a book, your entire hand, and notice how each creates its own unique pattern of light and darkness on the wall. Now imagine replacing that flashlight with the sun, your hand with the Earth, and the wall with the region of space where the Moon orbits. The same principles that govern shadows in your room apply on cosmic scales, but with a few beautiful complications that create the different types of eclipses we can witness from our small world. The sun is not a point source of light like a distant star or a small flashlight bulb. Instead, it's an enormous glowing sphere, nearly 1,000,000 miles across, that creates what astronomers call an extended light source. When an extended light source illuminates an object, it doesn't create a simple, sharp-edged shadow. Instead, it creates a shadow with two distinct regions, a dark inner core called the umbra, and a lighter outer region called the penumbra. Think of it this way. Imagine you're standing outside on a partly cloudy day when the sun is partially hidden behind a cloud. You're not in complete darkness. That would be like being in the umbra of the cloud's shadow. Instead, you're in a region of dim light, where some of the sun's rays still reach you while others are blocked. This is similar to being in the penumbra, where the light source is only partially obscured. Earth casts both types of shadows into space. The umbra is the cone of complete darkness that extends about 870,000 miles behind our planet, a region where the Earth completely blocks all direct sunlight from the sun's bright disk. Surrounding this dark core is the much larger penumbra, a cone of partial shadow where Earth blocks only part of the sun's light. From within the penumbra, an observer would see the sun as a crescent, with Earth taking a bite out of the solar disk. These two shadow regions create very different eclipse experiences. When the moon passes through Earth's penumbra alone, we get a penumbral lunar eclipse, a subtle event where the moon dims slightly but remains clearly visible and retains its familiar silver colour. Many people don't even notice penumbral eclipses unless they know to look for them. The moon becomes a bit fainter, as if a thin veil had been drawn across the sky, but it doesn't undergo the dramatic transformation that makes lunar eclipses so memorable. When the moon enters Earth's umbra, however, something remarkable happens. Cut off from direct sunlight, the moon should theoretically disappear entirely, becoming invisible against the black sky. But instead of vanishing, the moon often glows with a deep red or orange light that can range from a subtle copper tint to a dramatic blood-red hue that makes it look like a glowing coal suspended in the darkness. This red glow reveals something beautiful about our home planet. Earth's atmosphere acts like a vast lens, bending and filtering sunlight around the edges of our world. When sunlight passes through Earth's atmosphere during a lunar eclipse, the air scatters away the blue wavelengths, while allowing the red wavelengths to bend around the planet and reach the moon. It's the same process that creates red sunrises and sunsets, but on a cosmic scale. The moon, sitting in Earth's shadow, is illuminated by all the sunrises and sunsets happening around the rim of our world at that moment. The intensity and colour of this red light depend on the state of Earth's atmosphere at the time of the eclipse. If the atmosphere is particularly clear, with little dust or cloud cover, more light reaches the moon and it glows with a bright copper or orange hue. If there are dust particles in the atmosphere from volcanic eruptions, fires or sandstorms, less light gets through and the moon appears darker and redder. In rare cases, when the atmosphere is very dusty or cloudy, the moon can become so dark during totality that it nearly disappears from view. This atmospheric effect means that no two lunar eclipses look exactly the same. Each eclipse is coloured by the specific conditions in Earth's atmosphere at that moment, making every eclipse a unique portrait of our planet's air and weather, painted across the face of the moon. Astronomers sometimes use this connection to study Earth's atmosphere by observing how it affects the light reaching the moon during eclipses. The geometry of Earth's shadow also explains why lunar eclipses unfold at the leisurely pace they do. Earth's umbral shadow at the moon's distance is about 5,700 miles across, more than twice the moon's diameter. This means the moon has plenty of room to travel through the shadow region, and it takes time to cross from one edge to the other. The entire eclipse process, from first contact when the moon begins entering the penumbra to fourth contact when it emerges completely, can last over 5 hours. Within this extended timeline, the most dramatic portion, totality, when the moon is completely within Earth's umbra, typically lasts between a few minutes and about 107 minutes. depending on the moon's exact path through the shadow. If the moon passes through the centre of Earth's umbra, totality can last for nearly 2 hours. If it just skims the edge of the umbral shadow, totality might last only a few minutes, or might not occur at all. The moon's orbital motion provides the timing for this celestial theatre. Our lunar companion travels around Earth at about 2,300 miles per hour, fast enough to circle our entire planet in just over 27 days, but slow enough that its journey through Earth's shadow unfolds at a pace that allows us to watch and appreciate each phase of the eclipse. There's something deeply satisfying about the predictability of eclipse geometry. Unlike weather, which can change unpredictably from day to day, or earthquakes, which can surprise us without warning, eclipses follow the precise mathematical laws that govern orbital mechanics. Astronomers can calculate exactly when eclipses will occur, how long they will last, and what they will look like from any location on Earth, not just years in advance, but centuries or even millennia. This predictability comes from the stable nature of the Earth-Moon-Sun system. The Moon's orbit around Earth, while slightly elliptical and subject to small gravitational perturbations from the Sun and other planets, follows well-understood patterns. Earth's orbit around the Sun is equally predictable. When you combine these orbital motions with the fixed speed of light and the known sizes of the Sun, Earth and Moon, eclipse prediction becomes a matter of precise but straightforward geometry and mathematics. Ancient astronomers discovered this predictability through careful observation and record-keeping. The Babylonians, observing eclipses for centuries, noticed that similar eclipses tend to repeat every 18 years, 11 days, and 8 hours, a cycle they called the Saros. This discovery meant that if you witnessed an eclipse, you could predict when a similar eclipse would occur nearly 2 decades later. The Saros cycle reflects the complex interplay between the Moon's orbital period around Earth, Earth's orbital period around the Sun, and the gradual rotation of the Moon's orbital plane in space. Modern eclipse calculations can extend these ancient insights across vast spans of time. We can calculate that the last total lunar eclipse visible from London occurred on a specific date and lasted a precise number of minutes. We can predict that residents of Tokyo will see a partial lunar eclipse on a particular future date, and we can describe exactly how much of the Moon will be covered by Earth's shadow. This mathematical precision transforms eclipses from mysterious supernatural events into predictable celestial clockwork. The three-dimensional geometry of eclipse shadows also explains why eclipses don't happen every month. The Moon orbits Earth roughly once every 29.5 days, cycling from new moon through full moon and back to new moon. If the Moon's orbit lay exactly in the same plane as Earth's orbit around the Sun, we would indeed see a solar eclipse at every new moon and a lunar eclipse at every full moon. But the Moon's orbital plane is tilted about 5 degrees relative to Earth's orbital plane around the Sun. This 5-degree tilt means that most of the time the Moon passes slightly above or below the line connecting Earth and Sun. During new moon, the Moon's shadow usually misses Earth entirely, passing through empty space above or below our planet. During full moon, the Moon usually passes above or below Earth's shadow, remaining fully illuminated by sunlight. Only when the Moon happens to be near the points where its orbital plane intersects Earth's orbital plane, the nodes, can eclipses occur. Eclipse seasons happen roughly every 6 months, when the Sun, Earth and the Moon's orbital nodes align properly. Each eclipse season lasts about 35 days, during which at least one eclipse will occur, and sometimes 2 or 3. The exact timing and type of eclipses depend on the precise alignment geometry during each season. The elliptical nature of both Earth's orbit around the Sun and the Moon's orbit around Earth adds another layer of complexity to eclipse geometry. When the Moon is at perigee, its closest approach to Earth, it appears slightly larger in our sky, and Earth's shadow appears slightly smaller relative to the Moon. When the Moon is at apogee, its farthest point from Earth, it appears smaller, and Earth's shadow appears relatively larger. These variations affect the duration and appearance of lunar eclipses, with eclipses occurring when the Moon is farther from Earth, typically lasting longer, because the Moon moves more slowly in its orbit and the shadow appears larger. Similarly, Earth's distance from the Sun varies throughout the year, affecting the size and darkness of our planet's shadow. When Earth is farther from the Sun, during Northern Hemisphere summer, our planet's shadow is slightly larger and darker. When Earth is closer to the Sun, during Northern Hemisphere winter, the shadow is slightly smaller and receives more scattered light around its edges. These orbital variations mean that each eclipse has its own geometric personality. Some lunar eclipses present the Moon passing through the very centre of Earth's umbra, creating long periods of totality with deep red coloration. Others show the Moon just clipping the edge of the umbral shadow, producing brief eclipses where only part of the lunar disk turns red, while the rest remains bright silver. Still others are penumbral eclipses where the Moon never enters the umbra at all, creating subtle dimming effects that casual observers might not even notice. The beauty of eclipse geometry lies in its perfect blend of complexity and predictability. The interplay of orbital mechanics, light physics, and atmospheric effects creates an almost infinite variety of eclipse experiences, yet all following mathematical laws precise enough that we can predict them with extraordinary accuracy. Each eclipse is simultaneously unique and part of a vast, repeating pattern that connects us to the fundamental rhythms of our solar system. Understanding this geometry helps us appreciate that eclipses are not isolated events, but part of the ongoing dance between worlds that has been unfolding for billions of years. Every eclipse is both a moment to enjoy in its own right and a visible reminder of the elegant clockwork that governs the motion of planets and moons throughout the cosmos. As we contemplate the mathematical precision behind eclipse shadows, we can begin to appreciate that not all eclipses are created equal. The subtle variations in geometry, orbital positions, and atmospheric conditions combine to create distinctly different types of lunar eclipses, each with its own characteristics and beauty. Some plunge the Moon into deep red darkness, while others barely dim its silver light, and still others create spectacular displays where only part of the Moon transforms while the rest remains bright. If you've ever watched clouds pass across the Moon on a partly overcast night, you've seen how the same bright disk can take on completely different appearances depending on what stands between it and your eyes. Sometimes the clouds barely dim the Moon's silver light, creating a soft halo around its edges. Other times, thick clouds might completely obscure it, leaving only a faint glow behind the darkness. In much the same way, lunar eclipses come in several distinct varieties, each creating its own unique transformation of our familiar nighttime companion. The type of lunar eclipse you witness depends entirely on the Moon's path through Earth's shadow system. Remember that our planet casts two shadows into space, the dark umbra, where Earth completely blocks the Sun's light, and the lighter penumbra, where Earth blocks only part of the Sun's disk. The Moon's journey through these shadow regions determines whether you'll see a subtle dimming, a partial transformation, or the complete red metamorphosis that makes lunar eclipses so memorable. Let's begin with the most subtle type, The penumbral lunar eclipse. During these gentle events, the moon passes through only Earth's penumbra, never entering the darker umbral shadow. From the moon's perspective, Earth would appear as a dark disk taking a bite out of the sun's bright face, but not covering it completely. This partial blocking of sunlight creates a subtle reduction in the light reaching the moon's surface. Penumbral eclipses are the wallflowers of the eclipse world. They're often overlooked because the change in the moon's appearance is so gradual and subtle that many people don't notice them unless they know to look. The moon doesn't change colour dramatically or disappear into darkness. Instead, it simply becomes a bit dimmer than usual, as if someone had placed a thin piece of frosted glass between you and a light bulb. The dimming is most noticeable toward one side of the moon, the side closest to Earth's umbral shadow. If you know where to look and when to look, you might notice that one edge of the moon appears slightly duller than the other, creating a gentle gradient across the lunar surface. Photographers often capture this subtle shading more easily than the naked eye can perceive it, their cameras revealing the delicate interplay of light and shadow that our eyes might miss. There's something quietly beautiful about penumbral eclipses, though they require a more attentive kind of observation. They remind us that astronomical events don't always announce themselves with dramatic fanfare. Sometimes the cosmos speaks in whispers, creating changes so gentle that they reward patient observation and careful attention. If you've ever noticed the moon looking slightly off on a particular night, without being able to identify exactly what seemed different, you might have been witnessing a penumbral eclipse without realizing it. Partial lunar eclipses offer more obvious drama. These occur when the moon passes through both Earth's penumbra and partway into the umbra, but not completely into the dark shadow. During a partial lunar eclipse, you can watch as a curved bite of darkness appears to take a chunk out of the moon, growing larger as the moon moves deeper into Earth's umbral shadow, then shrinking again as it emerges. The edge of this dark bite is always curved because it's the shadow of Earth's spherical shape projected onto the moon's surface. Ancient Greek astronomers recognized this curved shadow as one of the first direct proofs that Earth is round rather than flat. No matter what time of night the eclipse occurs or what season it happens in, Earth's shadow on the moon always shows the same gentle curve, the shadow of a sphere. Partial eclipses can range from barely noticeable events where only a tiny sliver of the moon enters the umbra, to dramatic displays where most of the lunar disk disappears into darkness, while a bright crescent remains visible. The brightness contrast during these events can be striking. The portion of the moon still in sunlight appears brilliantly silver, while the part in Earth's shadow may glow with a dim red light, or appear almost invisible against the night sky. These partial events often provide some of the most photogenic moments in eclipse watching. The sharp boundary between the bright and shadowed portions of the moon creates compelling visual compositions, and the gradual progression as the shadow moves across the lunar surface provides a sense of cosmic motion that you can observe in real time. You're watching the shadow of your own world sliding across the face of another world, a direct visual reminder of how planets and moons move through space. But the most spectacular type of lunar eclipse is the total lunar eclipse, when the moon passes completely through Earth's umbral shadow. These are the events that have inspired the most mythology, caused the most fear in ancient peoples, and continue to draw crowds of observers to parks and rooftops around the world. During totality, the familiar silver moon disappears entirely, replaced by a glowing orb that can range in colour from bright orange to deep red to dark brown, or occasionally to such a dark hue that it nearly vanishes from view. The transformation during total lunar eclipses happens in distinct phases, each with its own character and beauty. First contact marks the beginning of the eclipse, when the moon first touches the edge of Earth's penumbral shadow. For perhaps an hour, the moon gradually dims as it moves deeper into the penumbra, though this phase is often too subtle to notice without careful observation. Second contact is when the drama really begins. This is the moment when the moon first touches the edge of Earth's umbral shadow, and a dark bite begins to appear on one side of the lunar disk. Over the next hour or so, this dark region grows larger as more of the moon enters the umbra. The contrast becomes increasingly striking as part of the moon remains brilliantly lit, while the shadowed portion glows with an increasingly noticeable red tint. Third contact marks the beginning of totality, when the last sliver of bright moonlight disappears and the entire moon enters Earth's umbral shadow. This is often the most magical moment of the eclipse. The harsh brightness that might have required you to squint when looking at the full moon is gone, replaced by a soft, otherworldly glow that you can gaze at comfortably for as long as you like. The colour during totality depends on Earth's atmospheric conditions at the time of the eclipse. When the atmosphere is particularly clear with little dust or moisture, the moon can glow a bright copper or orange colour that seems to emanate its own warm light. When there's more dust or haze in the atmosphere, perhaps from volcanic eruptions, wildfires or sandstorms, the moon appears darker and redder, sometimes taking on the deep crimson hue that has inspired the term blood moon. In rare cases, when Earth's atmosphere is particularly dusty or cloudy, the moon can become so dark during totality that it's difficult to see with the naked eye. These dark eclipses create an eerie effect where the moon seems to disappear from the sky entirely, leaving only the stars visible in what should be a moonlit night. Volcanic eruptions are particularly effective at creating these dark eclipses, as they inject fine ash high into the atmosphere where it can scatter and absorb the light that would normally reach the moon. The duration of totality varies significantly from eclipse to eclipse, depending on the moon's exact path through Earth's shadow. When the moon passes through the very centre of the umbra, totality can last up to about 107 minutes, nearly 2 hours of red moonlight. When the moon just barely passes through the umbra, totality might last only a few minutes. Most total lunar eclipses fall somewhere between these extremes, with totality lasting between 30 minutes and an hour. During totality, something wonderful happens to night vision. With the bright moon no longer overwhelming the darker sky, stars that were previously invisible become clearly visible. The Milky Way, if it's positioned properly in the sky, might become apparent in a way that would be impossible during a normal full moon night. It's as if someone dimmed the cosmic streetlight, allowing you to see deeper into the universe than you normally could during a full moon. Fourth contact marks the end of totality, as the first bright sliver of normal moonlight emerges from Earth's shadow. The process then reverses, with the bright portion of the moon gradually growing larger as the red shadow shrinks. Fifth contact occurs when the moon completely exits the umbra, returning to its normal silver appearance, and sixth contact marks the end of the penumbral phase, when the moon has completely escaped Earth's shadow system. The entire process, from first contact to sixth contact, typically takes about 5 hours. This leisurely pace is one of the great advantages of lunar eclipses over their solar counterparts. You don't need to travel to a specific location or worry about precise timing. If you're on the night side of Earth when a lunar eclipse occurs, you can simply step outside and watch the entire show unfold at nature's own unhurried pace. Each type of lunar eclipse offers its own rewards for observers. Penumbral eclipses teach patience and attention to subtle changes. Partial eclipses provide clear evidence of orbital mechanics in action, showing Earth's curved shadow moving across another world. Total eclipses offer the full spectacle of cosmic alignment, transforming the familiar moon into something that seems to belong in an alien sky. The frequency of these different eclipse types follows patterns that reflect the complex geometry of the Earth-Moon-Sun system. In any given year, Earth typically experiences between 2 and 5 lunar eclipses of all types combined, though many of these might not be visible from your particular location. Total lunar eclipses are less common than partial or penumbral eclipses, occurring about once every 2 or 3 years on average, though they might be visible from your location much less frequently. The irregular timing of lunar eclipses means that eclipse watching becomes a kind of astronomical patience game. You might see several eclipses within a few years, followed by a longer period with few or none visible from your location. This unpredictability adds to the sense of excitement when a good eclipse is predicted for your area. It might be several years before another comparable event comes your way. Modern eclipse prediction allows us to know exactly what type of eclipse will occur and how it will appear from any location on Earth. We can calculate whether the moon will pass through the center of Earth's shadow or just skim its edge. We can predict the duration of totality, the likely color of the eclipsed moon based on typical atmospheric conditions, and the exact times when each phase will begin and end. This predictive power transforms eclipse watching from a matter of luck into a planned celebration. Amateur astronomers mark their calendars years in advance for particularly favorable eclipses. Photography enthusiasts scout locations and prepare equipment for the perfect eclipse shot. Families plan gatherings around eclipse viewing, turning these astronomical events into shared experiences that connect us to the broader rhythms of our solar system. Yet for all our ability to predict and categorize different types of lunar eclipses, each one remains unique. The exact color during totality, the clarity of the sky, the presence or absence of clouds, the company you share the experience with, all of these variables combine to make each eclipse a distinct memory. 2 total lunar eclipses might follow identical geometric paths through Earth's shadow, but they will still create different experiences for the people watching them. As we contemplate the different varieties of lunar eclipses, we begin to appreciate how these celestial events have appeared to human eyes throughout history. Long before we understood the geometry of shadows or the physics of atmospheric refraction, people were looking up at these same transformations of the moon, trying to make sense of what they were seeing and creating stories to explain these mysterious changes in the night sky. Picture yourself stepping outside on a clear night when the moon hangs bright and full above you. The familiar silver disk bathes everything in soft light, the sidewalk beneath your feet, the trees lining your street, the gentle shadows they cast across your yard. This is moonlight as you've known it your entire life. Steady, reliable, comforting in its predictability. But tonight is different. Tonight, Earth's shadow is reaching across space toward the moon, and you're about to witness one of the most beautiful transformations in the natural world. The first sign that something extraordinary is beginning often comes not from any dramatic change in the moon itself, but from a subtle shift in the quality of the night around you. If you know an eclipse is coming, and you've been watching carefully, you might notice that the moon seems just a touch dimmer than usual, as if someone had placed the faintest filter between you and that bright disk above. This is the moon entering Earth's penumbral shadow, the first gentle touch of the eclipse beginning. For perhaps an hour, this subtle dimming continues, so gradual that if you weren't expecting it, you might not notice it at all. The moon doesn't change colour yet, doesn't show any obvious signs of transformation. It simply becomes a bit less brilliant, like a light bulb operated by a dimmer switch that someone is turning down so slowly You can barely perceive the change from moment to moment. Then, if you're watching carefully, you'll see something that never fails to catch the breath. A small, dark curve begins to appear on one edge of the moon. It's subtle at first, just a slight flattening of the moon's perfect circular outline, but within minutes it becomes unmistakable. Something is taking a bite out of the moon. This dark curve has a particular quality that sets it apart from anything else you might see in the sky. It's perfectly smooth, perfectly round, the shadow of your own world projected across space onto another world. As you watch, this dark bite grows larger and larger. The curved shadow creeps across the lunar surface with the steady persistence of a slow tide, revealing features and textures on the moon that you might never have noticed before. The sharp boundary between light and shadow creates a three-dimensional effect that makes the moon look more like the sphere it truly is, rather than the flat disk it usually appears to be in our sky. During this phase, you might find yourself checking the time, surprised by how quickly or slowly the eclipse seems to be progressing. Time takes on a different quality during lunar eclipses. Sometimes minutes feel like hours as you watch the shadow's imperceptible but steady progress. Other times you look away for what feels like a moment, only to look back and discover the shadow has advanced noticeably across the lunar surface. If the eclipse is total, the most remarkable moment comes when the last sliver of bright moonlight disappears and the entire moon enters Earth's shadow. This transition from partial to total eclipse can happen surprisingly quickly, sometimes within just a few minutes. One moment you're watching a thin crescent of silver light, and the next moment, that harsh brightness is gone entirely, replaced by something so alien and beautiful that it hardly seems like the same object you've been watching. The totality phase of a lunar eclipse creates an atmosphere unlike anything else in amateur astronomy. The moon, now completely in Earth's shadow, glows with a soft light that doesn't hurt your eyes to look at directly. You can gaze at it comfortably for as long as you like, studying details and colours that would be impossible to see during a normal full moon. The harsh glare that usually requires you to squint when looking at the full moon is replaced by a gentle luminescence that seems almost intimate in its softness. The colour during totality can vary remarkably from eclipse to eclipse, and even during a single eclipse the hue might shift and change as the moon moves through different parts of Earth's shadow. Sometimes the moon glows with a bright copper colour, warm and rich like a penny held up to firelight. Other times it takes on deeper red tones ranging from the colour of rust to brick to deep burgundy. In rare cases, the moon can appear so dark during totality that it becomes difficult to see against the star-filled sky. This red coloration has a quality that seems to come from within the moon itself, as if our familiar satellite had suddenly become a glowing coal suspended in space. The light is soft and diffuse, lacking the sharp shadows that normal moonlight creates. Instead of the crisp, high-contrast illumination of a full moon night, eclipse light creates a dreamy, almost underwater quality to the world around you. During totality, something wonderful happens to your night vision and your perception of the sky. With the bright moon no longer overwhelming everything around it, stars that were previously invisible begin to emerge. The night sky reveals depths that remain hidden during normal full moon conditions. If the Milky Way happens to be positioned favourably, it might become visible for the first time in weeks or months, arching across the sky like a river of faint light. Planets that were washed out by the moon's brightness suddenly become apparent. Jupiter might reveal itself as a steady yellow-white point of light. Mars could appear as a distinctly reddish spark. Venus, if it happens to be visible, might shine with startling brilliance against the darker sky. It's as if the eclipse has turned down the cosmic streetlight, allowing you to see deeper into the universe than a normal full moon night would permit. The silence during a total lunar eclipse often feels different from ordinary nighttime quiet. Perhaps it's psychological, the awareness that you're witnessing something rare and special, but many observers report a sense of heightened attention and calm during totality. The usual sounds of the night continue: insects chirping, distant traffic, the rustle of leaves in a breeze. But these familiar sounds seem to take on a different quality under the red light of the eclipsed moon, as if the world itself is participating in the cosmic event unfolding above. Temperature changes during lunar eclipses are typically subtle, unlike the dramatic cooling that can occur during solar eclipses. You might notice a slight drop in temperature as the eclipse progresses, but this is usually more due to the normal cooling that happens during nighttime hours than to any effect of the eclipse itself. The moon's influence on Earth's temperature is minimal compared to the sun's, so lunar eclipses don't create the dramatic environmental changes that make solar eclipses so physically apparent. Photography during lunar eclipses presents unique opportunities and challenges. The soft light of the eclipsed moon allows for longer exposures that can capture both the lunar disk and surrounding stars in the same frame, something that's usually impossible during a bright full moon. The changing colours and brightness levels throughout the eclipse provide a range of photographic possibilities, from the stark contrast of partial phases to the subtle, warm tones of totality. Many observers find that lunar eclipses create a sense of shared experience that extends beyond their immediate location. Unlike solar eclipses, which are visible only from narrow paths on Earth's surface, lunar eclipses can be seen by anyone on the night side of our planet. As you watch the moon turn red above your backyard, millions of other people across your hemisphere are seeing exactly the same transformation. This shared viewing creates a sense of global connection, a reminder that we're all passengers together on the same world, all looking up at the same sky. The emotional impact of witnessing a total lunar eclipse often surprises first-time observers. There's something deeply moving about watching our familiar moon undergo such a complete transformation. The event unfolds slowly enough that you have time to contemplate what you're seeing, Earth's shadow falling across another world, yet dramatically enough that the visual change is unmistakable and beautiful. Children often react with particular wonder to lunar eclipses. The transformation is obvious enough for young eyes to follow, gentle enough not to be frightening, and slow enough to hold their attention without requiring the precise timing that makes solar eclipses challenging for families to observe together. Many parents report that lunar eclipses become treasured memories, shared moments of cosmic wonder that connect families to the broader universe. As totality draws to a close, you might notice the first hint of normal moonlight beginning to emerge from one edge of the red disk. This moment, called fourth contact, marks the beginning of the eclipse's end. Just as the transition into totality could happen surprisingly quickly, the emergence from totality can also seem sudden. One moment you're looking at the soft red glow of the totally eclipsed moon, and the next, a brilliant sliver of silver light appears, so bright after the gentle eclipse light that it might make you blink. The return to normal proceeds in reverse order from the eclipse's beginning. The crescent of bright moonlight grows larger as more of the moon emerges from Earth's umbral shadow. The contrast between the bright, silvery portion and the dimly glowing red portion creates some of the eclipse's most visually striking moments. Gradually, the red glow fades from the portions of the moon that have emerged from the umbra, returning to normal silver as they enter only the lighter penumbral shadow. Within an hour or two after totality ends, the moon returns to its familiar appearance, bright and silver, and seemingly unchanged from any other full moon night. The transformation you witnessed might almost seem like a dream, except for the lingering sense of wonder and the memory of colours that seem too beautiful to be real. The moon that terrorized ancient peoples with its mysterious transformation now hangs peacefully in your sky, as familiar and comforting as ever. Many eclipse observers find that the experience creates a lasting change in how they perceive the moon during normal nights. Having seen it transformed by Earth's shadow, having watched it glow with the light of all Earth's sunrises and sunsets simultaneously, the familiar silver disk carries new meaning. It's no longer just a bright light in the night sky, but a world that participates in a cosmic dance with your own planet, sometimes stepping into Earth's shadow to create moments of extraordinary beauty. The memory of a total lunar eclipse often includes not just the visual transformation, but the entire experience of standing under the night sky and feeling connected to the motion of worlds. You've witnessed direct evidence of orbital mechanics, seen the curve of your own planet's shadow, and observed how Earth's atmosphere can paint another world in shades of copper and red. These sensory memories, the soft red light, the enhanced visibility of stars, the sense of cosmic connection, often inspire people to pay more attention to astronomical events in general. Having experienced the beauty of one eclipse, many observers find themselves drawn to learning about upcoming eclipses, meteor showers, planetary alignments, and other celestial events that connect us to the broader universe. As the eclipse ends and normal moonlight returns, you might find yourself already looking forward to the next time Earth's shadow will reach across space to transform our familiar satellite. The experience of witnessing a lunar eclipse creates a kind of cosmic anticipation, an awareness that the dance of worlds continues whether we're watching or not, but that occasionally the timing aligns perfectly to create these moments of shared wonder under the night sky. These personal experiences of lunar eclipses connect us to thousands of years of human observers who have looked up at the same transformations, trying to understand what they were seeing and creating stories to make sense of these mysterious changes in the familiar moon. Throughout history, different cultures have developed their own explanations and meanings for these celestial events, weaving lunar eclipses into the rich tapestry of human mythology and understanding. Imagine stepping into the sandaled feet of an ancient Babylonian scribe, climbing the steps of a ziggurat on a warm summer night around 750 BCE. The air carries the scents of burning oil lamps and the distant murmur of the city below, while above your head the full moon hangs like a silver coin against the star-scattered sky. You carry with you a stylus and a soft clay tablet, ready to record whatever the heavens might reveal. You have no knowledge of shadows cast by worlds, no understanding of Earth's atmosphere bending sunlight around our planet's curved edge. All you know is that sometimes, rarely, mysteriously, the familiar moon that guides your calendar and lights your nights transforms into something that looks like a glowing ember floating in the darkness. As you watch, a subtle darkness begins to creep across one edge of that bright disk. Your hand moves steadily across the clay tablet, pressing cuneiform characters into the soft surface. In the 17th year of Nabonassar's reign, on the 15th day of the month Adar, the moon was eclipsed. You don't understand what causes this transformation, but you know it's important enough to record with the same careful precision your predecessors have used for generations. This is how humanity's systematic study of the cosmos began, not with grand theories or sophisticated instruments, but with careful observers standing under ancient skies, watching the familiar become mysterious, and finding the patience to record what they saw. These early astronomers, working without telescopes or precise clocks, nevertheless managed to create detailed records that would eventually unlock the mathematical precision underlying all celestial motion. The clay tablets they left behind, preserved in the ruins of ancient libraries, reveal minds grappling with cosmic mysteries using nothing but careful observation and mathematical intuition. One tablet from ancient Babylon describes a lunar eclipse visible on March 19, 721 BCE, recorded with such meticulous detail that modern astronomers can use it to study the moon's motion with remarkable precision. The scribe noted not just that the eclipse occurred, but how long it lasted, what colour the moon became, and which stars were visible near the eclipsed moon during the event. Picture yourself as that ancient observer, stylus in hand, watching as the familiar silver disk slowly transforms into something copper-red and alien. You time the event using water clocks and the rising of particular stars, noting each phase of the eclipse with the devotion of someone who understands that the heavens speak in patterns, even if the language remains partially mysterious. Your observations will become part of a growing archive, a collection of careful records that future generations will use to discover the mathematical cycles governing when eclipses occur. Centuries later, in the warm climate of ancient Greece, other minds would build upon these Mesopotamian foundations with characteristic Greek love of geometry and logical reasoning. Picture Aristotle around 350 BCE, perhaps standing in the olive groves outside Athens on a clear night when a lunar eclipse was beginning. As he watched Earth's shadow creep across the moon's bright face, he noticed something that would provide one of history's first scientific proofs of our planet's true shape. The shadow's edge, moving slowly across the lunar surface, was always curved, perfectly, consistently curved, regardless of when the eclipse occurred or what position the moon occupied in the sky. Aristotle realized that only a spherical object could cast such a consistently round shadow from every possible angle. If Earth were flat, as many still believed, its shadow would sometimes appear as a line rather than a curve. But night after night, eclipse after eclipse, the shadow retained its circular arc. This moment represents something profound in human intellectual history, the realization that careful observation of celestial events could reveal fundamental truths about the world beneath our feet. The eclipse wasn't just a mysterious dimming of the moon, it was direct evidence of Earth's geometry, visible to anyone with the patience to watch and the wisdom to understand what they were seeing. A century later, the Greek astronomer Aristarchus stood under similar skies, but his mind was focused on a different puzzle. As he timed how long it took for the moon to pass completely through Earth's shadow, he was essentially measuring the relative sizes of the Earth and Moon using nothing but patient observation and geometric reasoning. Picture him with his water clock and astrolabe, carefully noting when the moon first entered Earth's shadow, when totality began, when totality ended, and when the moon finally emerged back into full sunlight. From these careful timings, Aristarchus could calculate that Earth must be roughly 3 times wider than the moon. His estimate wasn't perfect. We now know Earth is about 4 times the moon's diameter, but the method was sound and the reasoning brilliant. By watching one world's shadow pass across another world, he had measured cosmic distances and sizes with remarkable accuracy for his era. Even more remarkably, the Greek mathematician Hipparchus used eclipse observations around 150 BCE to calculate the actual distance from Earth to the Moon. Imagine the coordination this required. Observers in different cities, Alexandria, Rhodes, Babylon, all watching the same lunar eclipse and carefully recording the exact local times when each phase occurred. By comparing these observations and noting the slight differences in timing and appearance from different locations, Hipparchus could use trigonometry to triangulate the moon's distance. His calculation, about 60 Earth radii from our planet's centre to the moon, comes remarkably close to the modern value of about 64 Earth radii. Picture the satisfaction he must have felt, realizing that careful observation and mathematical reasoning could reach across hundreds of thousands of miles of empty space, to measure distances no human could ever travel. Meanwhile, on the other side of the world, Chinese astronomers were developing their own rich tradition of eclipse observation, motivated by different cultural beliefs, but driven by the same human curiosity about celestial patterns. In the imperial court of ancient China, eclipse predictions weren't just academic exercises, they were matters of political importance, since eclipses were seen as potential omens reflecting the harmony or discord between earthly rulers and the cosmic order. Picture a Chinese court astronomer during the Han Dynasty, perhaps around 100 BCE, standing in the Forbidden City on a night when a lunar eclipse was expected. He carries silk scrolls and carefully prepared ink, ready to record not just the eclipse's occurrence, but its colour, duration, and the precise hour when it reached maximum darkness. His observations will be preserved on silk and bronze, becoming part of an astronomical archive that extends back over 1,000 years. These Chinese observers discovered something remarkable through their patient record-keeping. Lunar eclipses follow a predictable cycle, with similar eclipses repeating every 18 years and 11 days. They call this the eclipse cycle, and its discovery allowed Chinese calendar makers to predict eclipses with accuracy that amazed visiting foreigners. Imagine the sense of cosmic understanding this must have provided, the realization that even the most mysterious celestial events follow mathematical patterns that human intelligence can decipher. As centuries passed, Islamic astronomers inherited and expanded upon these Greek and Chinese traditions, working in observatories from Cordoba to Baghdad to Samarkand. Picture al-Battani around 900 CE, standing on the roof of his observatory in Syria, using an astrolabe to measure the precise position of the eclipsed moon against the background stars. His observations would refine eclipse calculations with unprecedented accuracy and help create navigation techniques that would guide traders and explorers across vast distances. The Islamic tradition of eclipse observation was particularly important for geography and navigation. By observing the same lunar eclipse from different cities and comparing the local times when various eclipse phases occurred, Islamic astronomers could calculate longitude differences between distant locations with remarkable precision. This technique allowed them to create more accurate maps of their vast empire and navigate more precisely across trade routes that stretched from Spain to Central Asia. Imagine the coordination required for such observations. Astronomers in Baghdad, Cairo, and Cordoba, all preparing to observe the same eclipse, each equipped with water clocks, astrolabes, and carefully prepared charts. When the eclipse occurred, each observer would carefully note the local time when the moon first entered Earth's shadow, when totality began, and when the eclipse ended. Months later, when these observations were compiled and compared, they would reveal the precise geographical relationships between cities separated by thousands of miles. One particularly significant eclipse occurred on June 2nd, 1133, visible across Europe and the Middle East. This eclipse was so dark that the moon nearly disappeared from view, leading to extensive commentary from chroniclers and astronomers across the medieval world. Picture observers from London to Constantinople to Baghdad, all watching the same moon fade to such deep red darkness that it became difficult to see against the star-filled sky. Modern analysis suggests this unusual darkness was likely caused by volcanic dust high in Earth's atmosphere from a major eruption, demonstrating how eclipse observations preserve information not just about celestial mechanics, but about Earth's environmental history. Those medieval observers, unknowingly, were recording evidence of global climate events through their careful eclipse notes. As the Renaissance dawned in Europe, astronomers like Copernicus, Tycho Brahe, and Johannes Kepler inherited this rich tradition of eclipse observation while adding new theoretical insights and improved instruments. Imagine Galileo around 1610 peering through his revolutionary telescope at an eclipsed moon, seeing for the first time the mountains and craters on its surface with unprecedented clarity. Through his lens, he could watch Earth's curved shadow pass across these lunar features, providing additional confirmation that both Earth and Moon are spherical worlds orbiting through space rather than flat disks suspended in celestial spheres. The development of accurate mechanical clocks in the 17th and 18th centuries revolutionized eclipse observation by allowing astronomers to time events with precision measured in minutes, rather than rough estimates based on water clocks and stellar positions. Picture an 18th century astronomer, perhaps Edmund Halley in London around 1715, sitting beside his pendulum clock during a lunar eclipse, carefully noting the exact minute and second when each phase began and ended. This improved timing accuracy made possible increasingly sophisticated calculations of orbital mechanics and geographical positioning. Throughout this long history, one thread remains constant: the sense of wonder that draws human beings to stand under dark skies and watch the familiar moon transform into something mysterious and beautiful. From Babylonian scribes pressing records into clay to Chinese court astronomers painting observations on silk, from Greek geometers calculating with remarkable precision to Islamic navigators mapping the world through eclipse timing, each generation of observers was driven by the same fundamental curiosity that motivates amateur astronomers today. These historical observers remind us that science progresses through accumulated patience rather than sudden revelation. No single eclipse unlocked all the secrets of celestial mechanics, but thousands of careful observations across many centuries gradually revealed the mathematical patterns underlying the motion of Earth, Moon, and Sun. Each observer contributed pieces to a vast puzzle that eventually revealed the clockwork precision governing our corner of the cosmos. When we watch a lunar eclipse today, we participate in an unbroken chain of human curiosity and systematic observation that stretches back over 3 millennia. The same moon that darkened over ancient Babylon and Athens and Baghdad continues to enter Earth's shadow above our heads, connecting us to countless generations of observers who looked up at the same transformation and decided to watch, to record, and to try to understand. Perhaps most remarkably, these careful scientific observations became interwoven with human culture and storytelling. As different civilizations developed their own myths and spiritual interpretations to help make sense of these mysterious celestial events that seem to threaten the very order of the heavens. Picture yourself sitting cross-legged on woven mats in an ancient Mayan courtyard, surrounded by the soft glow of torches flickering against limestone walls. The air is warm and humid, heavy with the scent of copal incense and the distant sound of night birds calling from the jungle canopy. Above your head, the full moon hangs like a silver mirror in the tropical sky, casting sharp shadows across the intricate carvings that cover every surface of the temple complex around you. An elderly priest, his face painted with blue and red pigments, his elaborate feathered headdress catching the torchlight, raises his arms toward the moon and begins to speak in a voice that carries the weight of generations. "Tonight," he says, "the moon will die and be reborn. The jaguar god of the underworld will devour our celestial companion, and we will watch as it bleeds in the sky above us. But do not fear, this death is necessary for renewal, just as the corn must die in the earth before it can sprout again in the spring. Around you, the entire community has gathered for this moment that occurs perhaps once in several years. Children press close to their grandparents, wide-eyed with wonder and perhaps a touch of fear. Warriors set aside their obsidian-tipped spears to join in the ceremony. Even the ball players, still dusty from their ritual games in the great court, have come to witness this cosmic drama that will unfold over the next few hours. This is how lunar eclipses lived in human imagination, long before we understood the mechanics of shadows and orbital motion as cosmic stories, where the fate of the moon hung in the balance, where the actions of earthly communities could influence the outcome of celestial dramas. Every culture that has ever looked up at an eclipsing moon has created narratives to make sense of what they were witnessing, and these stories reveal something profound about the human need to find meaning and purpose in the mysterious events we observe around us. As the eclipse begins and that first dark bite appears on the moon's bright edge, the Mayan priest begins a chant that has been passed down through generations of sky watchers. The words speak of cosmic cycles, of death and rebirth, of the eternal struggle between light and darkness that governs not just the heavens but all life on earth. The community joins in, their voices creating a rhythmic accompaniment to the celestial drama unfolding above. They understand, in ways our modern minds sometimes struggle to grasp, that they are not passive observers of this event, but active participants in maintaining the balance of the universe. The Mayan interpretation of lunar eclipses as death and rebirth reflects a sophisticated understanding of natural cycles that goes far beyond simple superstition. These were people who had calculated the length of the solar year to within minutes of our modern measurements, who had tracked the motions of Venus with extraordinary precision, who understood that celestial events followed predictable patterns that could be calculated and anticipated. Their mythological framework wasn't ignorance. It was a way of embedding scientific knowledge within cultural practices that ensured the information would be preserved and transmitted across generations. As the eclipse reaches totality and the moon glows with that otherworldly red light, the ceremony reaches its climax. Priests burn precious jade and scatter flower petals, while the community makes offerings of food and drink to ensure the moon's successful resurrection. The red color, which we now understand comes from Earth's atmosphere, bending sunlight around our planet's edge, becomes in Mayan interpretation the blood of the cosmic jaguar's feast, the necessary sacrifice that allows renewal and regeneration to occur. Half a world away, in the mountain villages of ancient Tibet, other communities develop their own profound interpretations of these same celestial events. Picture yourself now in a high valley where the air is thin and crystal clear, where monasteries cling to cliffsides like the nests of mythical birds. The moon seems closer here in the rarefied atmosphere, its light more intense, its transformation during an eclipse more dramatic, against the backdrop of snow-capped peaks that stretch endlessly toward the horizon. Tibetan Buddhist monks, draped in their maroon and saffron robes, gather in the courtyard of their monastery as news spreads that an eclipse is beginning. They carry brass bowls and wooden drums, bells that have been cast with sacred mantras, and long horns that will send their voices echoing across the valleys. But their response to the eclipse is fundamentally different from the protective noise-making found in many other cultures. Instead of trying to frighten away a cosmic predator, they see the eclipse as an opportunity for spiritual practice and merit-making. In Tibetan Buddhist cosmology, eclipses occur when the demon Rahu attempts to devour the moon, but rather than seeing this as a purely negative event, they understand it as a time when the normal karmic effects of spiritual practice are multiplied many thousandfold. Prayers offered during an eclipse, they believe, generate far more positive karma than the same prayers offered during ordinary times. The temporary darkening of the moon creates a spiritual opening, a moment when the barriers between ordinary consciousness and enlightened awareness become more permeable. As the eclipse deepens and the moon takes on that mysterious red glow, the monks begin a practice session that will last for the entire duration of the event. Their chanting fills the mountain air with ancient Sanskrit syllables, each sound carefully chosen for its spiritual power and meaning. They're not trying to rescue the moon from a cosmic predator. They're using the moon's transformation as a mirror for their own inner work, seeing in the celestial death and rebirth a reflection of the spiritual transformation they seek to achieve in their own minds and hearts. The disciplined precision of their practice during the eclipse reflects a deep understanding that extraordinary celestial events call for extraordinary spiritual responses. These monks have calculated the eclipse timing as carefully as any modern astronomer, not just to satisfy scientific curiosity, but because they believe that spiritual practice must be precisely aligned with cosmic rhythms to achieve its full effectiveness. The eclipse becomes a focal point for community meditation, a shared opportunity for spiritual advancement that strengthens both individual practice and collective wisdom. In the forests of northern Europe, among peoples who live so intimately with natural cycles that their survival depended on reading the subtle signs of seasonal change, lunar eclipses took on meanings deeply connected to concepts of cosmic balance and renewal. Picture yourself in a clearing surrounded by ancient oaks, their massive trunks disappearing into the darkness above, their roots extending deep into earth that has supported this forest for thousands of years. A small community of perhaps 30 or 40 people has gathered around a central fire, their faces lit by the dancing flames, while above them the full moon begins its mysterious transformation. The elder who leads this gathering is someone whose knowledge extends back through generations of oral tradition, someone who carries in memory not just the stories, but the careful observations that give those stories their power. She speaks of the world tree, the cosmic axis that connects the underworld, the middle world where humans live, and the upper world of gods and spirits. The moon, in this cosmology, travels along the branches of the world tree, and during eclipses, it passes through regions where different spiritual forces hold sway. See how the moon grows dark, she says, gesturing toward the reddening disk above. It travels now through the realm of the ancestors, through the deep roots of the world tree where the wisdom of all who came before us is preserved. When it emerges, it will carry back to us the knowledge and blessing of those who walked this path in earlier times. This interpretation transforms the eclipse from a moment of cosmic crisis into an opportunity for ancestral communication and wisdom transmission. The community uses the eclipse time for storytelling, sharing the oral histories and practical knowledge that ensure survival through the long northern winters. Children learn from elders about hunting patterns and seasonal changes, about the medicinal properties of forest plants, about the social customs that maintain harmony within the group. The eclipse becomes a natural focus for the cultural practices that preserve and transmit essential knowledge across generations. The red colour of the eclipsed moon takes on special significance in this northern European context, associated with the life-giving blood that flows through all living things, the sacred red ochre used in burial ceremonies, the iron-rich earth that supports the great trees. Rather than seeing the red as a sign of cosmic violence, they interpret it as evidence of the life force that connects all things in the vast web of existence. The moon's temporary transformation reminds them that all apparent stability contains within it the seeds of change, that death and renewal are part of the same eternal cycle that governs everything from the changing seasons to the lives of individual human beings. As the eclipse reaches totality and the entire community falls into contemplative silence, broken only by the crackling of the fire and the distant calls of night birds, they experience something that our modern urban lives rarely provide: a direct, immediate connection to cosmic rhythms and natural cycles. The eclipse becomes a moment of profound communion with forces larger than individual human concerns, a reminder that they live within systems of meaning and purpose that extend far beyond the boundaries of their small community. These diverse cultural responses to lunar eclipses, Mayan ceremonies of death and rebirth, Tibetan practices of spiritual amplification, Northern European celebrations of ancestral wisdom, share common threads that reveal something fundamental about human nature. Across all cultures and time periods, people have recognized that eclipses represent moments when the ordinary order of things is temporarily suspended, creating opportunities for experiences and insights that would be impossible during normal times. The universality of these responses suggests that lunar eclipses touch something deeper than mere curiosity about astronomical phenomena. They seem to activate ancient psychological and spiritual responses that connect us to our prehistoric ancestors, who also looked up at darkening moons and felt the need to create meaning, ceremony, and community around these extraordinary events. The specific stories change from culture to culture, but the underlying recognition that eclipses represent liminal moments, thresholds between ordinary and extraordinary states of being, appears to be universal. Even in our contemporary scientific age, many people report that witnessing a lunar eclipse generates feelings and insights that go beyond intellectual understanding of orbital mechanics. There's something about watching the familiar moon transform into an alien red orb that seems to activate deeper patterns of consciousness, creating space for reflection, wonder, and connection that our busy modern lives rarely provide. The eclipse becomes a natural invitation to step outside the rush of daily concerns and remember our participation in much larger cosmic patterns. This continuity of human response across cultures and centuries suggests that lunar eclipses will continue to inspire new forms of cultural expression and spiritual practice as long as human beings look up at the night sky. Each generation finds its own ways to honor and interpret these celestial performances, but they're all participating in an ancient human tradition of recognizing that some experiences are too profound to be fully captured by rational explanation alone. The stories, ceremonies, and cultural practices that surround lunar eclipses serve as bridges between scientific understanding and lived experience, helping us integrate intellectual knowledge about orbital mechanics with the emotional and spiritual responses that these events naturally evoke. They remind us that human beings need both precise information and meaningful narratives, both accurate prediction and opportunities for wonder and reflection. As we consider these rich cultural traditions that have grown up around lunar eclipses, we can begin to appreciate how modern scientific methods have built upon this ancient foundation of careful observation and cultural meaning-making, using sophisticated instruments and mathematical techniques to unlock secrets about eclipses that would have seemed magical to earlier generations of observers. Picture yourself standing in the control room of a modern observatory on a mountaintop in Chile, surrounded by banks of computer monitors glowing softly in the darkness. Outside, the massive dome of a research telescope rotates silently on its precision bearings, tracking the moon as it begins its journey into Earth's shadow. But this isn't the patient, contemplative eclipse watching of ancient astronomers. Tonight, this telescope and dozens of others around the world are participating in a coordinated scientific campaign that will use the eclipse to unlock secrets about our planet's atmosphere, the moon's composition, and the precise mechanics of orbital motion with a precision that would have seemed magical to earlier generations of observers. The scientist beside you adjusts a spectrograph, an instrument that can break apart moonlight into its component colours with extraordinary precision, revealing the chemical fingerprints hidden within those familiar silver rays. During the eclipse, as Earth's atmosphere filters and bends sunlight around our planet's edge to create the red glow of the eclipsed moon, this instrument will analyze exactly how our atmosphere affects different wavelengths of light. In those subtle color variations lies information about the density and composition of air layers hundreds of miles above your head. Modern scientific study of lunar eclipses began in earnest during the 18th and 19th centuries, when improvements in telescope optics and the development of precise chronometers allowed astronomers to make increasingly accurate measurements of eclipse timing and appearance. But it was the invention of photography in the mid-1800s that truly revolutionized eclipse research, providing permanent records that could be studied and compared across multiple eclipses. Imagine the excitement in 1858 when the British photographer Warren de la Rue successfully captured the first photograph of a lunar eclipse. For the first time in human history, an eclipse could be preserved exactly as it appeared, studied at leisure and compared with future events. That first eclipse photograph, taken with a primitive camera and glass plate, opened the door to systematic photometric studies, precise measurements of how the moon's brightness changes during different phases of an eclipse. These early photographic studies revealed that lunar eclipses were far more complex than they appeared to casual observation. Different parts of the moon didn't darken uniformly as they entered Earth's shadow. Instead, the brightness varied in complex patterns that reflected the moon's surface composition, the geometry of Earth's shadow at different distances from the shadow's center, and the way our atmosphere scattered and absorbed different colors of sunlight. By the early 20th century, astronomers were using lunar eclipses as natural laboratories for studying Earth's atmosphere. During an eclipse, sunlight passing through our atmosphere at the very edge of our planet, through the thin shell of air that separates day from night around Earth's circumference, gets bent and filtered before reaching the moon. By analyzing the color and intensity of this filtered light, scientists could learn about atmospheric composition, density, and the way different gases absorb specific wavelengths of light. Picture yourself now in the laboratory of an atmospheric physicist in the 1920s, surrounded by glass prisms, photographic plates, and careful drawings of spectral lines. She's studying photographs from the previous month's lunar eclipse, comparing them with earlier eclipse images to track subtle changes in how Earth's atmosphere affects the light reaching the moon. What she discovers will contribute to our understanding of how atmospheric composition varies with altitude, season, and solar activity, knowledge that will prove essential for early aviation and eventually for space exploration. These studies revealed that not all lunar eclipses produce the same red coloration, and that these differences contain information about global atmospheric conditions at the time of the eclipse. Eclipses following major volcanic eruptions tend to be much darker and redder than normal, as volcanic ash and sulfur compounds high in the atmosphere filter out more of the sunlight, trying to reach the moon. By comparing eclipse brightness and colour across many years, scientists could track the global effects of volcanic activity and begin to understand how particles in the upper atmosphere affect Earth's climate. The development of electronic instruments in the mid-20th century opened new possibilities for eclipse research. Photoelectric photometers could measure lunar brightness with precision far exceeding what was possible with photographic plates, allowing astronomers to detect subtle variations in how different parts of the moon reflected the filtered light during eclipses. These measurements revealed that the moon's surface composition varies significantly from place to place, with some regions containing minerals that reflect red light more efficiently than others. Imagine sitting in mission control at NASA during the Apollo era, watching as astronauts on the moon's surface prepare to observe an eclipse of Earth. From the lunar perspective, our planet appears as a dark disk, surrounded by a brilliant ring of red light, all the sunrises and sunsets occurring around Earth's circumference at that moment, compressed into a thin, glowing circle. The Apollo astronauts' descriptions of these Earth eclipses provided a unique perspective on our planet's atmosphere and confirmed theoretical calculations about how Earth's shadow would appear from the moon. Modern eclipse research has become increasingly sophisticated, using instruments and techniques that can extract extraordinary amounts of information from the simple act of watching our planet's shadow cross the moon. Laser ranging experiments, begun during the Apollo missions and continued today, use lunar eclipses as opportunities to make precision measurements of the moon's distance and orbital motion. By bouncing laser beams off reflectors placed on the lunar surface by Apollo astronauts, scientists can measure the moon's distance to within a few centimeters and track subtle changes in its orbit over time. These laser measurements have revealed that the moon is gradually drifting away from Earth at a rate of about 3.8 centimeters per year, roughly the same rate at which your fingernails grow. This discovery confirmed theoretical predictions about tidal friction between Earth and Moon, and provided direct evidence for the slow evolution of the Earth-Moon system over geological time. Eclipse timing measurements contribute to this research by providing precise data about the Moon's position at specific moments, helping scientists model the complex gravitational interactions that govern orbital evolution. Contemporary atmospheric research uses lunar eclipses as natural probes of our planet's upper atmosphere in ways that would be impossible with artificial satellites or weather balloons. During an eclipse, sunlight passes through atmospheric layers at altitudes where direct measurements are extremely difficult to make. By analyzing the spectrum of eclipse light with modern instruments, scientists can detect trace gases, measure temperature and pressure variations, and study atmospheric chemistry at altitudes of 50 to 100 kilometers above Earth's surface. Picture yourself now in a modern atmospheric research laboratory, surrounded by computer workstations displaying real-time spectroscopic data from telescopes around the world, all focused on the same eclipsed moon. The instruments are detecting absorption lines from ozone, water vapor, carbon dioxide, and dozens of other atmospheric constituents, creating a detailed chemical profile of Earth's upper atmosphere. This information helps scientists understand how our atmosphere responds to solar radiation, how it varies with season and latitude, and how it might be changing due to human activities or natural climate cycles. Some of the most intriguing modern eclipse research focuses on detecting subtle variations in the moon's surface properties using multi-wavelength observations during eclipses. Different minerals reflect infrared and visible light differently, and these differences become more pronounced during the controlled lighting conditions of an eclipse. By photographing eclipses through various color filters and comparing the results, scientists can map the distribution of different rock types across the lunar surface with remarkable precision. The discovery of water ice at the moon's poles has added new dimensions to eclipse research. Scientists now use lunar eclipses to study how temperature changes affect these ice deposits, monitoring infrared radiation from polar regions during eclipses to understand how quickly lunar ice responds to the temporary reduction in solar heating. This research has implications for future lunar exploration missions that might rely on polar ice as a source of water and rocket fuel. Modern eclipse prediction has achieved accuracy that would astonish ancient astronomers. Contemporary calculations can predict eclipse timing to within seconds, eclipse magnitude to fractions of a percent, and the geographic visibility of eclipses for thousands of years into the future. This precision comes from detailed mathematical models that account for the moon's complex orbital motion, Earth's rotation and shape, and even subtle effects like atmospheric refraction that can shift eclipse timing by small amounts. The computational power available to modern astronomers allows them to model eclipse phenomena in extraordinary detail. Computer simulations can predict not just when and where eclipses will occur, but exactly how they will appear from any location on Earth, accounting for factors like atmospheric conditions, observer altitude, and local topography. These models help scientists design observation campaigns, plan eclipse expeditions, and interpret eclipse data with unprecedented precision. Space-based observations have opened entirely new perspectives on lunar eclipses. Satellites orbiting Earth can observe eclipses from vantage points impossible from the ground, photographing the moon's passage through different parts of Earth's shadow and monitoring how Earth's atmosphere affects sunlight at various altitudes. These observations provide three-dimensional information about eclipse phenomena that complements ground-based studies. The Hubble Space Telescope has used lunar eclipses for an unexpected purpose, studying the composition of Earth's atmosphere as a proxy for detecting atmospheres around planets orbiting other stars. During a lunar eclipse, astronomers can analyze the light spectrum of our own planet's atmosphere in ways that simulate how we might detect and study the atmospheres of distant exoplanets. This research helps develop techniques for the ultimate goal of finding potentially habitable worlds around other stars. Citizen science has found an important role in modern eclipse research. Amateur astronomers around the world contribute valuable eclipse observations, particularly photometric measurements and color estimates that help professional researchers understand regional variations in atmospheric conditions during eclipses. These amateur contributions are especially valuable because they provide geographic coverage that would be impossible for professional observatories alone to achieve. The coordination of global eclipse observation campaigns represents one of the finest examples of international scientific cooperation. When a lunar eclipse occurs, observatories from Australia to Chile to Europe all focus their instruments on the same event, sharing data in real time and coordinating their observations to maximize scientific return. These campaigns require precise timing, careful instrument calibration, and extensive communication between research groups around the world. Modern eclipse research has also revealed unexpected connections between lunar eclipses and other areas of science. Studies of how eclipse light interacts with Earth's magnetic field have provided insights into space weather and the way solar radiation affects our planet's electromagnetic environment. Eclipse observations have contributed to our understanding of how cosmic dust in the inner solar system scatters sunlight, and how this dust might affect climate and atmospheric chemistry over long time periods. The development of digital imaging has revolutionized eclipse photography, allowing scientists to capture detailed images throughout the entire eclipse sequence and analyze brightness and color variations with precision impossible in the film era. Modern eclipse images reveal subtle details in the moon's surface features, variations in eclipse color across different parts of the lunar disk, and even evidence of atmospheric phenomena like high-altitude clouds that can affect eclipse visibility. Perhaps most remarkably, modern eclipse research has come full circle in some ways, returning to questions that interested ancient astronomers while applying contemporary tools and techniques. Just as Aristarchus used eclipse timing to estimate the Earth-Moon distance, modern scientists use laser ranging during eclipses to refine our knowledge of lunar orbital mechanics. Just as medieval astronomers used eclipses to test their calendar calculations, contemporary researchers use eclipse predictions to verify and improve their mathematical models of celestial motion. The precision of modern eclipse science would seem magical to ancient observers, but the fundamental human curiosity that drives this research remains unchanged. Whether it's a Babylonian astronomer carefully timing an eclipse with a water clock or a contemporary scientist analyzing eclipse spectra with computer-controlled instruments, the underlying motivation is the same: to understand the mechanisms that govern the cosmos and our place within it. This sophisticated scientific understanding enhances rather than diminishes the wonder of eclipse experiences, knowing that the red light of an eclipsed moon carries information about Earth's atmospheric composition, that eclipse timing reveals subtle details of orbital mechanics, and that these events connect us to research efforts spanning centuries adds layers of meaning to the simple act of looking up at the darkening moon. As we continue to refine our scientific understanding of eclipses through increasingly sophisticated instruments and techniques, we're also creating new opportunities for people around the world to participate in eclipse observation and to experience the wonder that has drawn human attention to those events throughout history. Picture yourself stepping outside on some quiet night in the future when a lunar eclipse is beginning, perhaps years from now, when the memory of these words has faded, but the sense of wonder they awakened still lives somewhere in your mind. The air carries the particular stillness that seems to accompany extraordinary nights, not quite silence, but hushed expectancy, as if the entire world is holding its breath in anticipation of what's about to unfold above. The moon hangs in your sky, still bright and familiar, but something in the quality of its light seems different tonight. Perhaps it's your imagination, or perhaps it's the first subtle touch of Earth's penumbral shadow beginning to dim that silver radiance. You find yourself settling into a comfortable spot, a chair in your garden, a blanket spread on the grass, or simply standing in your driveway with your face turned upward toward the vast dome of night. As you watch, that first dark curve begins to appear, and suddenly you're not just an observer, but a participant in something that connects you to every human who has ever looked up at a darkening moon. The ancient Mayan priest who saw the cosmic jaguar beginning its celestial feast, the Chinese astronomer carefully noting the eclipse timing on silk scrolls, the medieval monk interpreting the red moon as a sign from the divine, the Enlightenment scientist using eclipse observations to measure the size of Earth. All of them are somehow present with you in this moment, part of an unbroken chain of wonder that stretches across centuries and cultures. There's something deeply moving about this realization that the same moon undergoing transformation above your head has been the source of stories and scientific discoveries and quiet contemplation for thousands of generations. The specific explanations have evolved, the instruments have become more sophisticated, but the fundamental human response remains unchanged. We look up, we wonder, and we find ourselves connected to something larger than our individual lives. As the eclipse deepens and that familiar silver light gives way to the otherworldly red glow of totality, you might find yourself thinking about the elegance of the geometry that makes this moment possible. 3 worlds, Earth, Moon, and Sun, aligned with mathematical precision across millions of miles of space, creating this gentle shadow play that has been repeating for billions of years. The same gravitational forces that hold planets in their orbits and keep galaxies spinning through the cosmos are choreographing this intimate performance above your neighborhood. Yet for all the scientific understanding we can bring to this moment, something about it remains irreducibly mysterious. The transformed moon hanging in the darkness seems to belong in someone else's sky, as if you've stepped through a doorway into a universe where the familiar rules no longer apply. This red orb glowing softly against the star-filled night carries within its light the atmosphere of your own world, all the sunrises and sunsets occurring around Earth's rim at this moment, bent and filtered by the air you breathe, then cast across space to illuminate another world. In this quiet hour of totality, with the harsh brightness of normal moonlight replaced by something you can gaze at comfortably for as long as you wish, the night reveals depths usually hidden by lunar glare. Stars emerge that were invisible moments before. The Milky Way, if it's properly positioned, might arch across the sky like a river of faint light. It's as if someone has dimmed the cosmic streetlight, allowing you to see deeper into the universe than is normally possible during a full moon night. This enhanced night vision during totality becomes a metaphor for eclipse experiences in general. They allow us to see familiar things in new ways, to notice beauty and pattern and connection that might otherwise remain hidden. The moon you've looked at thousands of times throughout your life reveals itself as something far more complex and wonderful than a simple light in the sky. It becomes a world with its own geography and history, a travelling companion that has been sharing Earth's journey around the Sun for over 4 billion years. A cosmic partner whose gravitational embrace helps stabilize the seasons and creates the tides that may have nurtured the emergence of life itself. As totality draws to a close and the first sliver of normal moonlight begins to emerge from Earth's shadow, you witness the reverse transformation, the alien red orb slowly returning to familiar silver brightness. But now that familiar light carries new meaning. You know that this moon has walked with humans through every chapter of our species' story, lighting the paths of hunters and gatherers, inspiring the first astronomers to track celestial cycles, providing the calendar systems that organized agricultural societies, and continuing to offer its gentle illumination to contemporary observers who look up from suburban driveways and city rooftops with the same sense of wonder that moved our earliest ancestors. The eclipse ends as gradually as it began, the moon slowly emerging from Earth's shadow system until it hangs bright and seemingly unchanged in your sky. But you have changed. You've witnessed something that connects you not just to cosmic mechanics, but to the long story of human curiosity and observation. You've participated in an experience that has inspired mythology and driven scientific discovery, that has brought communities together and provided solitary contemplation, that has remained constant even as civilizations have risen and fallen beneath its gentle light. Perhaps most remarkably, you've experienced a moment of cosmic intimacy, a time when the vast scales of astronomical distance and geological time compress into something immediate and personal. The moon that seemed impossibly distant moments before has revealed itself as close enough for Earth's shadow to reach, close enough for atmospheric light to paint with colours that seem almost supernatural in their beauty. This sense of connection between Earth and Moon, between individual observer and cosmic pattern, between contemporary understanding and ancient wonder, lies at the heart of what makes lunar eclipses so enduringly meaningful. They remind us that we live in a universe where beauty operates on every scale, from the quantum dance of particles to the majestic spiraling of galaxies, and that human consciousness is perfectly positioned to appreciate this beauty when we take time to notice it. The patient rhythms of eclipse cycles connect us to timescales that dwarf human history while remaining accessible to direct observation within individual lifetimes. The same mathematical precision that allows us to predict eclipses centuries in advance governs the formation of crystals, the migration patterns of birds, the structure of DNA, and the behavior of subatomic particles. We live within systems of pattern and meaning that extend from the most intimate details of our cellular biology to the grandest architecture of the cosmos. In learning to appreciate lunar eclipses, we practice a kind of attention that enriches all observation. We learn to notice subtle changes in familiar things, to find significance in gradual transformations, to value experiences that unfold at their own pace rather than according to human schedules. These skills of patient observation and contemplative attention serve us well beyond astronomy, helping us notice beauty and pattern and meaning in many aspects of life that reward careful attention. As you make your way back inside after the eclipse has ended, carrying with you the memory of silver light transformed to otherworldly red and back again, you're also carrying something less tangible, but equally valuable, a renewed sense of participation in the ongoing story of Earth and Moon and Sun, a deeper appreciation for the mathematical elegance underlying natural phenomena, and perhaps most importantly, a reminder that wonder is always available to those who know how to look for it. The Moon will continue its patient orbit, following the same gravitational pathways that have guided it for billions of years, occasionally passing through Earth's shadow to create these moments of cosmic theatre for anyone alert enough to notice. And you, having once experienced the transformation of familiar moonlight into something mysteriously beautiful, will never look at the moon in quite the same way again. Sleep well, fellow traveller in the cosmic deep. In your dreams tonight, may you find yourself drifting beneath skies where familiar moons transform into glowing embers, where Earth's shadow reaches across space to paint other worlds in shades of copper and crimson, where the patient mathematics of orbital motion creates beauty that connects the most intimate human experiences to the grandest scales of space and time. The universe continues its ancient dance of light and shadow, and the moon, our faithful companion, our cosmic timekeeper, our gentle reminder that we are never truly alone in the darkness, keeps watch over a world where curiosity and wonder transform distant lights into sources of meaning, connection, and endless possibility in the vast, patient night. This is the Sleepy Astronomer, wishing you the most peaceful rest beneath the gentle glow of moonlight and starshine, and reminding you that you too are part of this cosmic dance of light and shadow, forever woven into the infinite story of the night sky.